Hello and welcome to the Operator Introduction to the Insight 100. This presentation is designed to familiarize you with this very high-frequency robotic ultrasound device. In the 1990s, Dr. Dan Reinstein, with others at Cornell University, conceived of this ultrasound device, and they called it the Artemis. Later, ArcScan Inc. purchased the Artemis and renamed it. Today, practices around the world are using the Insight 100. This 50 megahertz very high frequency robotic ultrasound delivers detailed images of the cornea and the entire anterior segment, including behind the iris. There are numerous clinical applications for the device. To gain expertise on the operation of the Insight 100, it's important to understand a few ultrasound basics. Ultrasound is any sound wavelength with frequencies greater than 20 kilohertz. It cannot be heard by humans. Ultrasound travels very well through a liquid medium. Dolphins, for example, use ultrasound to communicate with each other, and they use it as a radar, similar to sonars on ships and submarines. In general, ultrasound applications are for cleaning, therapeutic, cuttings, and of course, diagnosis. They are going to differ from one another by the power and the cycles that they use. Diagnosis ultrasound does not generate heat, it has very low power and has high frequency. Most of our body can be evaluated with ultrasound because the body is roughly 80% water. So, for example, we can use ultrasound to examine a fetus, the heart, and many other areas of the body. Because the eye is full of fluid, the eye is a perfect organ to analyze with ultrasound. Ultrasound is created with a piece called the piezoelectric transducer. This is the foundation of ultrasound. It's a crystal. It gets excited and vibrates with electricity. The piezoelectric has the ability to emit sound and receive the echo being returned from the organ or the tissue that we're examining. So it converts electricity into sound waves, which then the instrument measures. A sound wave or vibration is sent out into tissues, and when a change in density is detected, the sound wave is reflected back as an echo. The same transducer listens for the echoes that are amplified and then displayed. Let's talk about a few technical concepts. First, the amplitude, which is considered the height of the peak. The higher the amplitude, the stronger the echo and the denser the tissue is. Next, the ultrasound wave also has a wavelength, which is the distance measured from crest to crest. And finally, the frequency is the number of these cycles per second. So a high frequency will have many of these peaks, and a low frequency will have fewer peaks. These frequencies are measured in hertz. For ultrasound of the eye, we use different frequencies depending on the area of the eye we're examining. The most popular ones are those that you have here on the screen. Generally, 40 and 50 megahertz frequencies are used for anterior UBMs. How does the frequency affect the image in the eye? Well, the higher the frequency is, the less penetration into the eye, and the greater the resolutions. When we're using ultrasound in the eye, we're balancing penetration, that is, how deeply can we get an image with really good image resolution. So you can see here that a 10 megahertz is going to image really deeply inside the eye, but it will not have the resolution that we want or need for the cornea as an example. In the case of the Insight 100, when we evaluate the cornea, we use a 50 megahertz probe, which allows us to see detailed structures like the epithelium and Bowman's membrane of the cornea. This is because the higher the frequency, the less deeply its sound can penetrate into the tissues, yes, but it also means that the resolution is better. Well, what is an A-scan? You're going to hear that term more as we talk about the Insight 100. It's important to understand why an A scan is the basis for any ultrasound. The A in A scan stands for amplitude, or the height of the peak, and it is a one-dimensional scan. Basically, one line or sound wave is projected from the front of the eye to the back of the eye. This sound wave will produce a peak or echo every time there's a change in density in its path. A sound wave is sent out, it finds a change in density and sends an echo back. The sound wave keeps traveling and encounters another change in density and sends an echo back, and so on. So if you use this image as an example, you're going to see that the A scan is the line below, or that blue line, and every time there's a change in density, you have a peak. You have a peak at the anterior cornea, and then another peak at the posterior cornea, a peak at the anterior lens, and another posterior lens, and finally a peak when you reach the retina. The A in A scan stands for amplitude, or the height of the peak. We also talk about B scans when we talk about ultrasound images. A B scan is a two-dimensional image. The B in B scan stands for brightness. We are measuring brightness. Imagine that we stack many individual one-dimensional A scans all together, one on top of the other. Every A scan has peaks which are creating a profile for the B scan. The stronger the signal, the higher the peak in an A scan, and the brighter the image in a B scan. So in this B scan image, we have thousands of one-dimensional A scans stacked one on top of the other. Scan at the specific point where you see the green arrow has the readout next to it. The peaks you see on that readout indicate each surface. The first peak is the epithelium, then the Bowman's membrane, and the endothelium. And the peaks of the A scan are translated to colors in the grayscale in the B scan. Those peaks correspond to the bright surfaces on the B scan. When we start to do imaging, there are a few factors that influence the quality of the images. One of the most important factors is what we call the angle of incidence. For the best quality scan, the probe needs to be perpendicular to the structure you're evaluating. This way, you have maximum feedback reflected back to the probe. The more perpendicular to the structure, the stronger the echo, the higher the peak, the brighter the surface, and the clearer the overall image. Another factor that affects the ultrasound is the surface of the tissue that we're evaluating. If the surface is small or smooth, you'll have a better image. If the surface is coarse or irregular, you get a scattered feedback. So for example, retina or cornea will give you a very clear image, but when you consider the ciliary body, it is more difficult to see, not only because of the size and position within the eye, but also because of their surface. Finally, we want to consider the beam focus. When we're scanning, we want to find the area of maximum resolution. The probe on the Insight 100 has a single focal area, which is where we have the maximum amount of resolution in an image. We refer to this as the focal plane. And all of those factors help to produce the incredible detailed images of the cornea and the anterior segment. Now let's look at the Insight 100 device in particular. Your system is comprised of the software and computer, a fluidics module, and an imaging module. First, the imaging module, or scan head, and within the scan head is the transducer probe. The probe is held in place magnetically and is computer controlled. The motors inside the device move the probe to maintain that best angle of incidence and the best beam focus, horizontally and vertically on the XY axis, toward and away from the eye on the Z axis, rotational, and the most important part of the insight is the arc motion parallel to the eye with a perpendicular probe position, all controlled by computer. Also inside of the scan head is a camera so the operator can view the patient's eye while scanning, as well as a fixation light for the patient. The next part of the full system is the fluidics module. As we learned earlier, we need a fluid medium through which the sound waves will travel. In our case, we have two fluids, distilled water, which does not come into contact with the eye, and saline, which does come into contact with the eye. Do that? Well, there is a disposable product called the eye seal, one per patient, that is attached to the front of the scan head. After the patient is positioned against the eye seal, the saline is released into the eye seal cup. So starting from the inside out, first you have distilled water within the scan head, the eye seal on the scan head, then saline in the eye seal cup, and the patient positioned against the eye seal. Next, a brief look at the software. The software has 8 main pages. The patient page is where demographic information is entered or recalled. After a patient has been scanned, a quick view of all those scans can be seen right from the patient page. The next tab, the scan page, is where you navigate to take a scan. Here, you'll see all the scans that have been acquired for this patient, as well as those that have been transferred to the final scan set for analysis. Analysis pages provide a larger view and the ability to use measuring tools. Here, you see the anterior analysis page and the cornea analysis page. Phakic IOL analysis includes a table that averages measurements, and the glaucoma page includes automated caliper measurement placement. Making up the final pages are the configuration page and the utilities page. The configuration page only appears when logged in as the administrator or service. This concludes the brief overview of the Insight 100. We'll take a deeper dive during your hands-on practical training.